Hi class, in this video we want to start looking at Chapter 14, which talks about our sun. And so in this chapter we'll talk about the basic properties of the sun, what you see when you look at it, how to explain some of those things, how the sun rotates, what it's made of, and then how we know about what's inside of the sun and what the different layers of the sun are, and then where is the energy ultimately coming from inside the sun. So this first section of this chapter talks about the basic idea of why does the sun shine, as well as some of the basic structure of the sun. So here's an image of the sun, not in visible light, but in something else that we'll come back to later. But you can see all this structure here. This is hard to see if you just look at the sun through regular visible light, because there's so much visible light. So you have to filter a lot of stuff away to see some of the finer details of what's going on. And you can see there are all these crazy things happening on the sun. It's just like a bubbling cauldron of gas. And so we'll talk about a lot of these different things here. These kind of arcs of gas coming off of it in these hot spots, these different places here where it looks really bright and hot. So why does the sun shine, though, in the first place? There were ideas early on as to why the sun shined. And of course, the first thing people thought of years and years ago was that it's just a ball of fire. And what is a ball of fire? What is a fire? Well, a fire is a chemical reaction. And so if you looked at the amount of material in the sun and thought about the sort of the chemical energy available for burning, for actual burning like you would have in your fireplace. Let's say you had a piece of wood and you're going to burn a piece of wood. There's a certain amount of chemical energy there that can go into heating your house. So if you try to calculate that with the amount of energy, with the amount of mass that you have there in the sun, and then you divided that total energy content by the rate at which the sun is producing energy, which is called its luminosity. So the luminosity is the energy per second that the sun is producing, joules per second. So if you divide the total amount of energy you have available by the rate at which it's being consumed or given off, what you find is that the sun should only last about 10,000 years. And we know that that's not true. The sun's been burning for a lot longer than that, and it's been very steady over the years, and so it seems as if it's going to last much longer than that. So it can't possibly be just a fire, like a chemical kind of process. So it's not on fire. Is it contracting? So in chapters 7 and 8, when we talked about the creation of the solar system, we talked about how the solar system started as a big ball of, not ball, but a big cloud of gas and dust out in space, and slowly gravity started contracting that cloud. And as gravity pulls something in toward other masses, everything speeds up. There's a conversion between gravitational potential energy and kinetic energy. And then that higher kinetic energy, that higher speed, is related then to the temperature. So is the sun hot because it's just gradually being squeezed by gravity? Well, again, you can look at the amount of mass and the size of the sun and what gravity could do in terms of contracting that and how much energy there is available to turn into sort of heat to be able to give off light from. And so if you calculate the total gravitational potential energy available, another form of energy besides chemical energy, if you calculate this gravitational potential energy available, divided by the luminosity, you get 25 million years. And that's a much bigger number, so maybe that's a little bit more of a possibility, but it's still pretty clear that the sun has been around for a lot longer than that for various reasons. We know this. So this can't possibly be a source, the ultimate source of the sun's energy. There must be something else. So what could that be? So it's not gravitational contraction. So what it really is nuclear power. It's nuclear energy. The sun is your ultimate nuclear power source. And so we'll talk about the reactions going on inside the core. So it's really only inside the very small core of the sun where these reactions are happening. And there's a type of energy that you might call nuclear potential energy. It's sort of stored energy in the nucleus. Really what it is when you take two nuclei, in the case of the sun, when you take two nuclei or some number of nuclei and form bigger nuclei, you get energy out. Energy comes out of that process. This is called nuclear fusion. We'll talk about this a little bit later. This is opposed to what happens in most of the reactors around the world that use nuclear energy. Those are nuclear fission reactors, where a large nucleus is broken up, like uranium, and energy is released in that as well. So sometimes you get energy as you're making bigger nuclei. Other times you get energy as you're breaking up really big nuclei. And there's a point in between where there's kind of a limit as to how big you can make the nucleus and still get energy out, or how small you can break something up and still get energy out. And we'll talk about those limits at a later time. So if you look at the total nuclear potential energy available in the core, just the core, divide that by the rate at which the sun is giving off its energy, you get something that's much more reasonable, something that seems to make sense compared to what we know about our sun and our solar system and such. And that's about 10 billion years. So the sun is about halfway through its lifetime of about 10 billion years. About a little over 4.5 billion years old now. So we don't have to worry at all about the sun running out of energy anytime soon. So it's got about another 5 billion years left to go. So what are some of the properties inside the sun that make this happen? What are some of the different things that have to be going on to make this happen, to allow the star, the sun, to be sort of stable and unchanging, or very little changing is happening over the last many, many years. So kind of like these people in this picture, there are some balancing acts going on inside the sun. And if you think about this person down here as being in the core of the sun, they are having to hold up the layers of the sun above them. So this person up here is kind of like at the outside layer of the sun. This person's sort of in the middle, and this person's at the bottom of the sun. This person on the bottom clearly has to support a lot more weight than the person in the middle. The person on the top doesn't have to support anything, it just sits there. And so there's sort of a gravitational force pulling down on the different layers of these people, or the different layers of the sun. And then these layers have to be pushing upward to support those layers on top. So there's this sort of what we might call a gravitational equilibrium, where gravity's trying to squeeze the sun to make it smaller, everything's trying to get closer to the center, but then there's some kind of pressure pushing outward to prevent the sun from getting smaller. So if we look at that in terms of the sun, again, all these layers here they have weight to them, and gravity's trying to squeeze everything. But the deeper you go into the sun, the more stuff there is above you, and so the more you have to support those higher up layers. And so the harder you have to push outward in order to support that. The harder gravity is pulling inward against you. So for the sun to maintain its shape, its size, there must be this gravitational equilibrium, where gravity, the inward force of gravity, is being balanced by some outward force from energy, basically pushing outward. So energy kind of pushing outward is sort of balancing gravity that's kind of pulling inward. And so if you think about what might happen if the sun were to suddenly turn off in the center, if it were to suddenly not produce any more energy in the core, if this core were to suddenly stop producing energy, we would lose, or at least if it were to slow down, we would lose some of this pressure, this outward pressure. And the core, because it's not producing as much energy, it's going to cool down. The core is going to cool. It might not be cold, but it's 15 million Kelvin right now. And we'll talk about temperatures, but let's say it cooled down by 1 million Kelvin. Well, that would at least slow down the rate of these reactions. There would be less energy coming outward. With less energy coming outward, gravity can squeeze a little bit more. So gravity will squeeze the star a little bit more, but that squeezing, that extra squeezing by gravity, will actually heat it back up again. And then with the heating back up, the nuclear reactions are going to then increase again, producing more energy now. That will be increasing the pressure then, pushing the star a little bit back outward against gravity again. So there's this balancing act going on. Gravity's trying to pull in pressure, the radiation pressure, the light pressure, energy pressure is pushing outward. And if one changes, the other one changes in response in such a way that the star remains stable for a very long time, until it runs out of fuel. Until it starts to run out of fuel in the core, the star remains very stable over a long period of time. So that last slide was like a gravitational equilibrium we said, and it's what helps maintain the shape of the star, the radius. There's also another kind of balancing act going on, and that's an energy balance. Energy is produced in the core. There's a certain amount of energy produced every second. Well, that has to go somewhere. It must go somewhere. It just can't sit there. So it gradually flows outward through these various layers, and ultimately it's given off at the surface in the form of visible light, as well as other wavelengths that we can't see, like ultraviolet and infrared. So there's this balancing act also with energy. The star has to be giving off only as much energy as it's producing. And if it produced more energy than it gave off, then there would be some energy building up in here, and that would probably cause the star to expand or change or something. So if the star isn't changing, if there's an equilibrium going on, then we know that whatever energy is being produced in the star every second, let's say, that's the same as what's being released every second. Otherwise, energy is being built up in the star, and then that would cause temperatures to increase, and probably the star would expand. One interesting thing, though, is that the energy that's produced in the core doesn't immediately escape. It takes a long time, thousands and thousands of years, and we'll talk about that in a minute. But it takes a very long time for the energy that's produced in the core to actually get out of the sun itself. There are several different processes going on that the energy kind of has to go through to get from the core outward to the surface. In the core, it's produced in the form of really, really high energy gamma rays. But by the time that energy in the form of gamma rays gets to the surface, it's more in the form of visible light. So there's a lot of absorption and re-emission and so on of the light as it escapes the sun. It turns it from gamma rays in the core to visible light at the surface. So there's a lot of processes going on, and it takes time. Even though light travels very fast, light isn't traveling just straight out of the sun. The gravitational contraction, we said, is what ultimately produces that energy from the beginning. If we go back to Chapter 8, that gravitational contraction was ultimately what produced the energy in the first place, the temperature in the first place, to get these nuclear reactions to start. Once those nuclear reactions started in the center, then all that energy, the energy being produced then was much higher, temperature got much higher, and the pressure pushing outward got much higher, and that slowed down the gravitational contraction of the star. And so, early on, the star was contracting, gravity was winning, making the star smaller and smaller. But eventually, when the nuclear reactions went on, when the nuclear fusion reactions went on, the contraction stopped, and the star established a particular size that it has maintained now for a very long time. So what does the star look like? What does our sun in particular look like? And our sun is a very average star, so other stars look very similar to our sun. What are the different layers that we can talk about? So this is just a picture. We'll go through these layers one by one and think about the different things that are happening in these different layers. So general properties, the sun has a radius of about 7 times 10 to the 8 meters. It's about 109 times the Earth's radius. So you can put about 109 Earths across the diameter of the sun. That's a lot. One Earth can fit inside of one of these sunspots. And these sunspots, we'll talk about them in more detail later, but those are like little storms on the surface of the sun. It's actually a little bit cooler there, and they look very dark, right? But they only look dark because they're surrounded by much hotter areas around them that are brighter. So if you were to take a sunspot and somehow remove it from the sun and just put it up in the sky, it would be as bright as the full moon. So it's still a very bright object. It's not technically black, but it looks very dark in contrast to the hotter regions around it. So the sun's radius is big. The mass is huge as well, about 300,000 times the Earth's mass. So you could put 100 Earths across the sun, just in terms of the size, about 109. Or you could take, in terms of mass, 300,000 Earths worth of mass, and that would be the mass of the sun. But the sun is mostly gas, hydrogen and helium primarily, not metals and rocks and stuff like that. And then there's this number, the luminosity, that we had mentioned before. Luminosity just means brightness. How much energy every second is the star emitting, giving off. And it's about 3.8 times 10 to the 26. 10 to the 26, that's a lot of zeros. This is joules per second. This many billions of billions of billions of joules per second. Okay, 10 to the 26, it's a big number, huge number. So the outermost layer of the sun is really not a layer at all. It's just called the solar wind. It's a flow of charged particles from the surface of the sun, and that solar wind extends out throughout the entire solar system. And it interacts with the planets. It causes things on the Earth like the northern lights. It interacts with the magnetic field of different planets. Causes northern lights and southern lights and so on other planets as well. It's just a stream of charged particles flowing from the sun. And it changes over time. It gets more and less concentrated in different directions depending on things that are going on the sun itself. So that's the solar wind. And then just inside the solar wind, the outermost layer of the atmosphere of the sun is called the corona. It's a very thin layer. The gas is not dense at all. It's very diffuse, but it's hot. And it seems strange. It's very, very hot way up above the surface of the sun. A lot of million Kelvin. It's very hot. If we then go a little bit further inside the corona, it's still not down to the main surface. There's the kind of the first layer of the atmosphere called the chromosphere. This is kind of like a pinkish layer. It looks a little pink. The temperature is pretty hot there as well, but certainly not as hot as the corona. It's about 10,000 to about 100,000 Kelvin. So it's very hot. It's hotter than the surface of the sun, but not as hot as the corona. So as you're getting closer to the sun from the corona to the chromosphere, you're actually cooling down. It's kind of strange, but it's true. So there's not a lot of gas up here, but the gas that there is in the corona is moving very rapidly. The temperature is very fast, very high. And then the chromosphere, it's more dense, still not as dense as the surface, but it's still higher density than the corona. And the temperature is much cooler, but still very hot. And then you get to the photosphere, and that's the main surface, the visible surface of the sun. You couldn't walk on it. It's not a solid surface. It's a gassy surface. You fall right through. But the temperature is much cooler than the chromosphere, but still very hot for you and me. So about 6,000 Kelvin, or maybe closer to maybe 5,800 Kelvin. Exactly the number, isn't that important, but on the surface is where these sunspots are. And so these sunspots are like blemishes on the surface of the sun, where there's some storms or things going on, and we'll talk about that. Also off the surface, you often get these what are called prominences, these big, almost like belches of gas that try to go out into space, but they get captured back down. Gravity pulls them back down. There's also a magnetic field with the sun that kind of helps move these charges. So when the sun kind of belches like this, these are all a bunch of charged particles that get thrown out into space. A lot of it comes right back down, and sometimes they follow magnetic field lines, so they have these nice arcs to them. So we'll look at these prominences later. Solar flares and prominences we'll look at. A typical sunspot can be as big as the Earth. One of these sunspots can swallow up the Earth. So they're not minor storms by any means. And the sun rotates too. The sun rotates because it's all part of the solar system that formed early on. The whole solar system was rotating, so the sun rotates too. And if you look at it from above, sort of the North Pole, it's rotating counterclockwise with everything else. But it rotates at different rates. It rotates at a different rate along the equator than it does near the poles, and so we'll look at that difference in rotation, and what effect that has on what's going on. And it rotates at different rates because it's a ball of gas. It's not a solid object like the Earth. So you can think of the photosphere almost like the crust of the Earth, the upper really thin layer of the surface of the sun. And down below that then is this convective zone. In this convective zone, energy that comes from the core is bubbling upward, kind of like water does in a pot of boiling water. You get this convection, this upward flowing of energy coming up, and as it rises up, it cools, and it gives off, and some energy escapes out into space as in the form of light. Then that gas cools and falls back down, and there's this continuous circulation of gas in the convective zone, very much like a pot of boiling water, where water bubbles up and then sinks back down. Or if you ever take a cup of coffee, what's interesting is if you like coffee and you like to put creamer in your coffee, take a nice hot cup of coffee with a little bit of cool creamer, maybe a teaspoon. Pour the creamer in off to the side maybe a little bit. Pour it down into the coffee, and that creamer at first is cool. It's a cool liquid, so it sinks right away because it's cool. But as it warms up, it tends to flow back to the top. And you can see that. You can actually see it come back up after you pour it in. You pour it in kind of gradually, not so fast that you create a lot of turbulence, but pour it in kind of gradually. It'll fall down and warm up as it falls, and then it'll rise back up because it's warmer. And then you might even see it sink back down again. It might go up and down a couple times. So that's an example of convection. You can even do this with hot water and a little drop of food coloring too. Take a cup of water, put it in the microwave, in a microwave safe cup, heat it up to a decent temperature, put one little drop of food coloring in, and you might see the food coloring sink right away and then rise up and then maybe go up and down a couple times, but the food coloring will also disperse very quickly because the water is so hot. So the convection zone is where energy is transported by convection, where gases are rising up and then falling back down. The falling back down gases pick up more energy, then they rise back up again. So it's a continuous process. And then inside the convection zone is the radiation zone. In here, it's so hot. It's so hot in the radiation zone. So again, actually, we didn't go back to the temperature of the convection zone. The convection zone is hot as well. It's hotter than the photosphere. And so now as you're going into the core of the sun, toward the core of the sun, temperature starts increasing again. So it's actually cool on the photosphere, 5,800 Kelvin or so. It's hot in the chromosphere. It cools off where the photosphere is. And then it starts getting hotter again as you go down deeper into the sun. It gets so hot in the radiation zone that light basically just passes straight through the material. The material, there aren't any atoms of any kind to absorb light and sort of trap it. So the light energy just flows right through. It's just totally ionized gas. It's a plasma, and so the light just passes right through. So we call this the radiation zone. And then once it cools, as the light is traveling upward, it's traveling to gradually cooler and cooler regions until it gets to the bottom of the convection zone, where it's cool enough for some atoms to exist where that energy then can actually be absorbed. Once that light energy is absorbed by gas, that gas kind of takes that energy in the form of like a speed. It increases the speed of the gas, and then that gas can flow upward. And so that hot gas carries with it the energy from the light that it absorbed ultimately. And, it's bumping into a lot of things as it goes, exchanging energy with other atoms and so on. And eventually these sort of hot atoms rise up. When they get to the top, they give off their energy and again sink back down to pick up more. And the cycle continues. So the radiation zone is a zone where the atoms are not formed correctly in such a way that they can absorb the light, so the light just passes through. And then the core, so this could be like 1,000,000 Kelvin down in here now, or 10, even like around 10 million Kelvin. It varies as you go away from the core. The core itself, though, is so hot. It's about 15 million Kelvin. And so in the core is where the nuclear reactions are taking place. That is ultimately where the energy is being formed by the sun, in that tiny little core inside the center of the sun. If you think about the amount of energy being produced, we had talked about that number, the luminosity, that 3.8 times 10 to the 26 joules every second. If you were to take that total energy that the sun is producing, and that's what it's producing in the nuclear reactions every second, it's giving that off at the surface eventually. When it's in equilibrium now, whatever it's emitting, whatever it's producing in the core, it's giving off. So it's giving off 3.8 times 10 to the 26 joules every second. If we were to take that amount of energy that the sun gives off in just 1 second, that could give the Earth as much energy as it needs for the next 500,000 years or so at its current energy consumption rate. So 1 second of energy produced by the sun is just an incredible amount of energy. 500,000 years of energy that we use on the Earth. So if we can harness that energy, there's plenty of energy there for us to use. So those are the main structures inside the sun. And we'll talk a little bit more about some of those, especially the core and the nuclear reactions in the next part. So in summary then, we have gravitational and chemical energy sources can't be what's going on, solely what's going on inside the sun, because if those were the only sources of energy, the sun would only last maybe 25 million years, and we know it lasts longer than that. Ultimately though, gravitational contraction did play a role because it's what helped form the sun, and that's ultimately what made the core hot enough to start nuclear fusion reactions. And so these nuclear fusion reactions are what really is powering the sun right now, and producing the energy that it is emitting every second. So then in the structure, just remember these areas. There is the solar wind, which is the very, very outside, sort of not even a layer of the sun, but it's sort of this wind blowing off the sun. And then going inward, you have the corona, then the chromosphere, and then the photosphere. And you're decreasing in temperature as you go to the photosphere. That's the visible surface. And then when you get below the photosphere, temperature starts increasing again in the convection zone, then ultimately in the radiation zone, and then ultimately in the core, about 15 million Kelvin in the core. There's a lot of good websites that you can go to as well. If you go to one of NASA's websites, there's a satellite called SOHO, the Solar and Heliospheric Observatory. And you can look at all kinds of information about the sun. You can look at sunspots. What does the sun look like right now? You can look at the sun in different wavelengths, so it takes pictures of the sun in terms of the X-ray light it gives off, or in terms of the ultraviolet light it gives off, and it's interesting to see the different looks that the sun has, the different faces of the sun in those different wavelengths. So if we click on the sunspot, this is March 5th, 2017. There's not much going on. It's a pretty quiet sun at the moment, but there is something over here that we could click on and get some information. But it shows, for a perspective, it shows the size of the Earth and the size of Jupiter down here. And there's a lot of other things you can click on real time. These are images of the sun right now, taken recently. There's a date here, March 7th. Well, no, that's not the date. That says it's going to be down. But if you click on one of these, it should give you the date when they were taken. So this is one place you can go. There's also something called a website called spaceweather.com. And this website gives you a lot of information, again, about what's happening with the sun. It talks about other, space weather related things as well, not just the sun. So here's again an image of the sun. It talks about sunspots. There aren't many there right now. It says the sun is blank, no sunspots. So it's very quiet right now on the sun. This picture down here is the current aurora oval, and this is the North Pole of the Earth right here. And so there's northern lights in this green band up here. There's always northern lights up there to some degree. Sometimes they're quiet, sometimes there's a lot of them, and it gives you a sense of where you might need to be on the Earth to see the northern lights. So this is a good, I like to keep an eye on this page to see if the green oval ever creeps down into the northern United States. Sometimes it does, and if it does, then you go outside, look to the north, and there might be a chance you could see some northern lights. So in the next part of Chapter 14, we'll talk a lot more about the nuclear reactions going on inside the sun.